All right, guys, recording is started again. Yeah, so again, I know we just had a long break, which is a good thing. So I'm just going to tell you guys that I'm not going to take this lesson on for too long as well, because it's a lot of new stuff. So we'll try and get through a decent amount. Right now, we're going to start with set theory. Okay, and we'll try to get through just the basics at least. But before we do that, one more thing to note about quantifiers, which nobody cares about, but we have to know it anyway, is that if you have a negation passed through a quantifier, it kind of acts like a negative sign. Like if we look at this up here, we see if we have the negation of some kind of mathematical statement, we can pass the negation through the quantifier all the way to the statement, which is represented by P here. And all it does is it changes universal to existential and existential to universal. So this upside down A becomes an E if we pass the negation through it. That's all this is telling us. And the opposite. If I pass the negation through this upside down E, it becomes the A support. So for every, it becomes they exists, or they exist becomes for every. Again, it's just another way to represent something, which I don't think we will ever need, but it's nice to know it in case it comes out in a multiple choice or something like that. So again, all it shows us is that the negation, which is the thing in front, can be passed through the quantifier and go all the way to the statement. And then all we have to do is change the quantifier. Okay, now so at least we're getting to set theory because that's a bit more interesting. It's a lot less memorizing that section. Yeah, we're getting to that. I think we might even get to see. Have you guys done set theory in high school? Oh. All right, so this learning unit really does have all the new stuff in it. Okay, so we define a set as an unordered collection of objects, which is a very abstract definition. So a set is just a collection of any objects. Like we have this example here, which shows us a set involving the elements 1, 2, and 3. In this case, it's numbers. But a set could be anything. I mean, instead of 1, 2, and 3, we have here Odin, Thor, and Loki, right? Anything. It doesn't matter. As long as it's a collection of objects written in this format, then it's a set. Okay, and to say that something belongs to a set, we use this term that looks like a small, well, not really a small, it's like a capital E, but a weird way of writing it. This one here means an element of. So this says A is an element of the set, which looks like this, containing A, B, and C. Just a way to say something belongs to a set. So I could have also said up here, I could say 1 is an element of A, for example. It means in the set A, 1 is one of the elements. I could also say 2 is an element of A. I could say 3 is an element of A, because all those things are elements of the set A. All right, does that make sense? Unfortunately, it does, yeah. Because the normal brackets will represent coordinates. Okay, so do you guys think I could say 4 is an element of A? Not true, right? So the way we would say this is 4 is not an element of A. So you write element and scratch it out. It means it's not an element of the set. Okay, so it's kind of like an equals to sign or not equals to. Similar idea. Okay, now we look at a set, which is a mess of just a whole lot of random objects. So this set here contains 4 elements. The first element is the number 1. The second element is the letter B. The third element is another set, right? That's allowed. You can have a set within a set. And the fourth element is what we call the empty set. It's a set with nothing in it. So this, again, that's why I said a set can be a collection of anything. Numbers, objects, sets, whatever, right? People's names, anything. So if I were to ask you guys how many elements are in the set, what would you guys tell me? 4, right? 4. Because we have to count the sets as well. We have to count everything. Some people count the elements in the set and then you count too many. So that's not what we do. We just count here. 1, 2, 3, 4. Everything separated by a comma. Or maybe I shouldn't say comma because even in the set there's commas. Just don't go a set within a set. Don't count things compounded, basically. Okay. All right, now what's the story here? Okay. So here we're looking at, you guys might have seen a double dot symbol before, I'm not sure. If you haven't, it just means such that. So I've written it here. If you see a double dot like that, it just means such that. So now we're looking at ways to use our quantifiers to rewrite the set above here, which as we can see is just the set of all the even numbers. Right? It's an infinitely long set. We can see it goes on forever. That's what the dot, dot, dot means. And what we're saying here is there's 2 ways to write this. One is obviously much easier than the other. The one at the bottom is we can write it as x such that x is even. That's the nice way to do it. So a messy way to do it is above here where we put the quantifiers and stuff together. So you guys can use the one at the bottom. That's okay. That's allowed. Anyone who's a bit more daring can use the one above. And we can try and read that. I mean, why not? Let's see if we remember what these things mean. So the one on top says, this is a set where x is an element of natural numbers. So that means x must be natural numbers such that there exists an n which is an element of natural numbers where x is equal to 2n. It's a very complicated way of saying a simple thing. Right? But we know the story here. 2n, just as we saw before with 2j, always gives you something even. If n is a natural number in this case, because we're only looking at positive numbers. Okay, again, if this confuses you, don't worry too much about it. Just give it a read when you go home. But again, this is allowed. The one at the bottom is fine if you prefer that. Yeah, right. That one's not so bad. Okay. Just remember that these are just ways to represent the set above here. Okay, now I'm going to give you guys some examples to try. Let me think whether I need to do one of these first. You guys want me to do one? Let's do one. Okay. So describe each of the following sets, both in words and by listing out enough elements to see the pattern. So the in words part, you don't have to worry about. All I want you guys to do is list out some elements so we can see a pattern. So in words, okay, so the first one is x such that x plus 3 is an element of natural numbers. Okay, so let me start with a 0 here first to make something a little bit easier. Let's suppose we said x such that x is an element of natural numbers. Right, and this one here is clear what needs to be done. X is an element of natural numbers, so that means this set will look like this. I'll write it like this. 0, 1, 2, 3. Sorry, natural numbers start from 1, right? Not from 0. So 1, 1, 2, 3, and so on. So question 0, that's what you write. That one is straightforward. But question 1 is a little bit more tricky. I'm going to show you guys how to think about something like this. So x plus 3 is an element of natural numbers. So it's kind of like we're shifting the list above by 3. It's a similar idea. And if anyone ever struggles with this, it's nice to list out a few elements to get an idea. So for example, the first natural number will be 0, right? So for that, I'll say x plus 3 is equal to 0. Solve for x, that will give you your first element. So if I solve for x here, I'll get x is equal to -3. The second element will go with the second natural number. According to the rule, that will be x plus 3 is given by the second natural number. Wait, sorry, I'm starting from 0 again, and I should start from 1, right? Okay, sorry. So forget the first one. X plus 3 is equal to 1, which is the first natural number. So solve for x here, we get 1 minus 3, which is -2. Then the second element will be x plus 3 is equal to 2. Solve for x here, you'll get 2 minus 3, which is -1. So what I'm listing on the right are the elements of my set. I'll just do one more so we can see a pattern. X plus 3 is equal to the third natural number, which is 3. In this case, x is 0. So these are the elements of my set on the right here, which will end up looking like -2, -1, 0, 1, 2, and so on. Oh, God, because we see the pattern at this point. Okay, does that make sense to you guys? So just follow the rule, equate it to everything in the set to get your actual elements. So you guys can give that a try for the next. Maybe just try the next one and let's see if we can get that. Then I'll talk with the rest. So, would you guys want me to do number 2 as well?
It's natural number. One.
Yes, we did 1. Let me write the answer since we did it. -2, -1, 0. Okay. Now, number 2 is just telling us from the answer above, because you can see this part here is the same as what we worked out above, right? By saying whatever the answer is, you only take the natural numbers from that answer. That's all it's saying, right? So basically take what's above. I'm gonna write it like this, just so we remember it. 0, 1, 2. And then from here, you just scratch out everything which is not a natural number. So only 1, 2, 3, and so on are the answer to this one. It's getting a bit messy here. Okay, so you guys can try 3 and 4. I see a 4 and an and here, which gets a bit weird, but let's see what we can do. Hopefully I remember how to do these ones. So I'm thinking I probably should do this one because it's a little bit tricky. Is anyone managing to get somewhere? You guys need more time. More time. Okay. Oh, take care of your misery. Okay, this one is even confusing me a bit, but we can just work through them step by step and see what's happening. So this is giving us two sets here. So let's write the elements from both of these sets and see where we end up. It would be nice if I had more space here, or I do. Okay. So for the first one, x is an element of natural numbers, which means that will give us the elements. Again, we can do it like we did before. We can say x is equal to the first natural number is 1, x is equal to 2, x is equal to 3, and so on. That's coming from the first bracket. The second bracket says negative x is an element of natural numbers, so that means negative x is equal to 1. Then we have to solve for x like we did before. So that means just x is equal to -1. Let me put a double dot there, that's weird. So similarly, the next one says negative x is the next natural number, which is 2. So x is -2. I'll just do one more, 3. X is -3. So this here comes from the first one. This comes from the second one. And that would have, one of these would have been our answer, but now this is separated by an downward triangle is an OR, separated by an OR. So that means our answer, our set must belong to this element, to this part here, or this part here. So in other words, we just list all of them together. Because if we do that, if our answer to this is written as just all of these, so it's going to basically be all the negative and all the positive numbers. So it'll be negative, or let me start it like this. Dot, 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 -2, -1, 0. No, there's no 0 because it's natural numbers, right? That keeps on catching me. 1, 2, 3, dot, dot, dot. Because if you look at our answer, everything here belongs to either this or this. So that's how from the answer we can see that what we did is correct. And just as we always do in these questions, we look at these, solve for x for each one, for every element of the set it's restricting us to. And from there, we formulate our answer. If there's a quantifier in between, we have to determine whether we include everything, whether we include a subset. Okay. So this is, yeah, this is a little bit tricky. Take some thinking. You guys want to try number 4 based on what I just did? Similar idea. I'll give you guys a minute to try that one. If you're not getting them, don't stress. It took me a while to understand this as well. You guys are seeing it immediately like this. So, sorry, question.
One, for example, the number 4 is asking us to join it, and number 3 is asking us to separate it. Who separates it?
Let me think. Number 3 is saying that x, yeah, or so whatever x you look at, it must belong to either this or that. So that's why the combined set must have everything. Yeah, yeah, exactly. So the last one will be it must belong to both. Whatever you look at must then belong to both. So that is there even going to be any elements there? Probably not, because nothing belongs to both those sets. You could put the symbol, or you could just write this open bracket, close bracket, whatever you prefer. Okay, so guys, for the last one, as we just mentioned here, the two sets that we work out from x element of natural numbers or negative x element of natural numbers, that's already been done for the previous question. right? The two lists are given here. So now the X or the elements of the set need to be, every element that we have needs to belong to both of these sets at the same time. So in other words, we're looking for common elements, common things between both these sets. And clearly there's nothing common between both of them. Right? These two sets are completely mutually exclusive. So the answer to this will just be, you can write the empty set if you want to, or you can write the symbol of an open bracket and a closed bracket with nothing inside it. Now, I promise you guys, the questions get nicer after this. This is just a very rapid, terrible introduction to the section. And this is not even the bulk of the marks. So it's good to know this, of course. But the bulk of the marks comes from all the stuff here, unions, intersections, which you've probably heard of before. Maybe. Okay, anyway, here's a summary of some of the sets we should know. We've probably seen all of these before. This zero scratch dot means empty set. We know the natural numbers, integers, rational numbers, and real numbers. We've seen all of these before. This is just showing us what symbols we use to represent them. Okay, this was I think learning unit 1 stuff. Just the different sets. Okay. So now relationships between sets. Okay, here this is vitally important. If I give you two sets, one is 1, 2, 3, the other one is 2, 1, 3. These sets in the way we look at sets theory, these two sets are completely equivalent. They're exactly the same. There's no difference. Because in sets, order does not matter. Right, so these two are completely the same. That's very important. Let me just highlight that part. These two are completely equivalent. Order does not matter in sets. Even this at the bottom here. These three different ways of representing the same set, completely equivalent. Order doesn't matter. You can separate things by adding, subtracting, whatever, as long as you're representing the same things. All right, so you can represent a 3 as 1 plus 1 plus 1. It doesn't matter. It's the same thing. Or you could represent it in, that's not Roman numerals, whatever, that's like a tally. You could represent things like that. It doesn't matter. As long as you, order doesn't matter and your representation style doesn't matter. It's like using variables kind of thing. Okay. Okay, now the word subsets, yeah. Subset and what's the other word? Let's see. Subset and okay, both of these refer to subsets, but one is like a proper subset. It's like the equivalent of less than or less than equal to. Right, so for the two sets above, A is given by that. Let's suppose I gave you another set, C is equal to 1, 2. Is that C a subset of A? Yes, it is, right? It's a perfect subset of A, so we could write that as C is a subset of A. But here's a question. Could I say C is a perfect subset of A? Can't say that, right? Because that's like a less than equals to kind of thing. So actually, I could say that, right? I could say that. I could say C is a perfect subset of A. But now suppose I changed C above and I made it 1, 2, 3 instead. Now, which of these two is still true? Both of them are still true, right? Okay, so we've not established the difference between this perfect subset yet. Think of an example where we can see that coming out. Okay, anyway, we'll get back to that in a moment. My head is not working right now. Perfect subset. Okay, we'll see this. Actually, no, there's the thing here. We wrote an example. Okay, so here's a set involving characters, and which of these two is true is what we're asking here. Yeah, that's definitely a perfect subset. The one at the top.
one of the critical is like saying 5 is less than 5.
Yes.
If 5 is less than equal to 5, then it makes sense because.
Yeah, so you're right. So that's the difference. Right? That's what we need to take away from this, is that this one here is not true because it's not less than or equal to in that way of speaking. The bottom, this line at the bottom is equal to, in a way. Comparing sets, you can show that these two are equal. These two are clearly equal, right? But this doesn't have the line at the bottom. Yeah. So that line is for sets that are equal. The subset is for a set which is clearly a smaller version of the big set. So that's the difference there. Okay, maybe at this point where clearly the brain is starting to fail slowly. I can give you guys an example to try, or do you want to do this homework? Homework. No one's going to even do this at home, guaranteed. But anyway, we work on the honor system here, so I'll give you guys this to try as homework. And yeah, then guys, have a good weekend. All right. You guys just like me because I'm lazy.
So do you prefer? Oh.
Yeah.
Then you go below.
Yeah, sure.